Flight 10 of SpaceX's Starship did not look like a dramatic comeback story or a Hollywood rocket launch, but for the people actually paying attention to the engineering, it quietly became the most important test in the program so far. For the first time, a full Starship stack went from ignition to staging to a long coast upper stage burn to re-entry and controlled splashdowns for both stages, without a total loss of the vehicle along the way. It was not flawless, and parts of the ship literally tore themselves apart, but that is exactly why the data is valuable. The launch profile at the start looked familiar. 33 Raptor engines on the Super Heavy booster lit in staggered fashion. The pad disappeared in a cloud of exhaust and dust, and the stainless steel tower of hardware began to rise. What stood out this time was how long the vehicle sat on the pad after ignition. For several seconds, it seemed to hover just above zero altitude, engines roaring, but translation barely starting. That is not hesitation. That is a deliberate test of structural load paths and thrust balancing, while the clamps still have some control. Once the clamps released and the booster cleared the tower, the ascent looked clean through the lower atmosphere. As the stack climbed toward thinner air, it passed through max Q, the point where aerodynamic loads are the highest on the structure. Just after that, one Raptor engine on the booster failed. At this altitude, losing an engine is a different problem than a ground misfire. The remaining engines have to compensate while the guidance system preserves the trajectory and keeps bending moments within margins, all without wasting the propellant that will be needed for the flip and landing burn later. The important thing is, what did not happen next? There was no obvious wobble, no visible yaw or roll that suggested control loss. From camera view, the plume pattern changed slightly, and then the rocket simply kept climbing. That is the autopilot and thrust vector control doing their job, proving that the booster can shrug off an engine loss during the most aerodynamically stressful part of the flight. It is exactly the kind of off-nominal condition that has to be demonstrated before any human cargo ever rides the stack. After main engine cutoff and hot staging, the upper stage continued towards space while the Super Heavy began its return. On Flight 9, SpaceX had pushed the booster's re-entry to a brutal high angle of attack, essentially flying the cylinder sideways to maximize drag. That created so much load that internal pipes feeding propellant to the engines bent, starving them and causing a violent breakup during the attempted landing burn. For Flight 10, the team dialed that angle back by a few degrees, still aggressive enough to gather data on thermal and structural behavior, but not enough to crumple the frame. As the booster dropped back through the atmosphere, grid fins and engine gimbals worked together to steer it toward its planned splash zone in the Gulf. When it came time for the landing burn, SpaceX intentionally set up a scenario that no simulation can fully answer. The same engine that had failed on ascent did not come back, so instead of relying solely on the 3 central Raptors, they lit an engine from the inner ring to share the load. The booster still held a clean attitude, hovered briefly just above the water, then shut down and fell like a steel elevator shaft into the ocean, detonating on impact. That final explosion looks wasteful only if you imagine this booster as a priceless artifact. In reality, it is a nearly obsolete V2 design, about to be replaced by a more capable V3 with upgraded Raptor engines. SpaceX has already performed soft splashdowns and hardware recoveries. They understand corrosion, fatigue, and refurbishment costs. What they needed more on Flight 10 was a hard answer to how the control system behaves when the symmetrical center engine landing pattern breaks, and whether the structure holds when you deliberately stress it on the way down. They bought those answers with metal they were going to retire anyway. While the booster was finishing its noisy experiment over the water, the Starship upper stage was busy checking off milestones that earlier versions had never reached. The ship completed its primary ascent burn, shut its engines down cleanly, and coasted in space without any immediate emergency. That alone is a first for this hardware family. During the coast phase, SpaceX finally demonstrated the PAZ dispenser-style payload deployment system in a realistic environment, sliding open the payload door and pushing out dummy Starlink satellites in a slow, controlled stream. The concept looks simple. A drum of satellites is rotated, and each unit is pushed out through the opening one at a time. In practice, the tolerances are tight, and clearances between spacecraft and door edges become very real at orbital velocities. One dummy spacecraft clipped the edge of the opening on the way out. A small bump that will show up in post-flight reviews and might lead to tiny adjustments in deployment timing or positioning. That is what test flights are for. The important thing is that the door mechanism, the internal carrier, and the control logic all functioned well enough to complete the sequence without jamming or ripping a vehicle apart. Even more critical than payload deployment was the Raptor restart in vacuum. Restarting a methane oxygen engine after it is cooled in space is a non-trivial maneuver. Propellant needs to be settled properly in the tanks. Turbo machinery must spin up without ingesting gas pockets, and ignition has to light off in a regime with no ambient air. A failed relight at this stage could mean a dead ship stuck in a decaying orbit, or a re-entry so uncontrolled that debris footprints become a safety issue. On Flight 10, the restart worked. Exhaust bloomed from the engine skirt, the ship adjusted its trajectory, and another major technical gate on the road to full orbit missions quietly opened. The real trial, though, was still ahead: re-entry. Previous Starship versions had seen severe damage and failure in their control flaps when slamming into the atmosphere belly first. The forward flaps were notorious weak points, suffering from heating, erosion, and plumbing issues that turned neat stainless steel into ragged edges. For V2, those forward flaps were redesigned with different internal routing and improved thermal protection. On Flight 10, they performed as intended. The front hardware survived the hottest part of entry without obvious burn-through. The rear flaps were a different story. Long before the ship reached peak heating, telemetry and camera footage showed one of the aft flaps starting to shed pieces. Thin stainless skin panels near the hinge line began to peel and flutter, evidence that some localized failure had already started. Later, as the vehicle pushed deeper into the atmosphere, gas venting through the engine section suddenly ignited or overpressurized, producing a bright, instantaneous flash under the skirt. The blast tore chunks of metal away and left one side of the aft hardware badly chewed up. Even after that blast, the vehicle remained controllable. Aerodynamic authority was degraded but not lost. The remaining flap area and body lift were enough to keep the belly-down attitude and guide the ship toward its target splashdown. On the way down, outside observers noticed something visual that was impossible to ignore. The ship's external appearance changed. The side that had launched with a black mosaic of heat shield tiles returned from re-entry looking half orange and half chalky white. The color shift was not a sign that the heat shield had failed wholesale. Post-flight imagery from SpaceX showed that the hexagonal pattern of tiles stayed largely intact, with clear outlines still visible. The explanation comes from how the tiles are constructed and how SpaceX prepared this particular ship. The primary ceramic tiles are mounted over a layer of white insulating material. In some test regions on this vehicle, they had deliberately removed tiles to expose that substructure and evaluate how it behaved under real re-entry conditions. As the ship slammed into the upper atmosphere, that exposed insulation charred, vaporized, and turned into fine white dust, which was then blown backward along the hull. That dust acted like glaze inside a kiln. It coated neighboring tiles and stainless surfaces, then baked into place under the extreme heating environment, leaving behind pale streaks and a distinctly whiter nose section. Mixed into that cloud was material from another experiment: metallic test tiles used in place of ceramic in select areas. Under attack by atomic oxygen in the upper atmosphere, those metals oxidized rapidly, creating reddish particulates. Carried along the flow over the ship's belly, those oxidized particles stained sections of the heat shield orange. What looked like a cosmetic surprise was, in fact, the visible footprint of multiple material experiments running simultaneously. By the time Starship reached denser air and prepared for its own landing burn over the ocean, it had already done more for the program's understanding of aerothermal loads and material response than several previous flights combined. Despite the damaged aft flaps and the brutal conditions, the ship managed to execute the flip maneuver and light its engines for a controlled splashdown near its intended target point. SpaceX later reported that the missed distance from the aim point was on the order of 3 meters. For a tower catch, that would still be outside acceptable limits. For a test article that had partially blown itself open on the way down, it is a remarkably tight shot. The outcome of Flight 10 leaves the program in a very specific place. The V2 stack has now demonstrated enough of the basic profile: engine out tolerance on ascent, aggressive but survivable booster reentry, alternative landing engine configurations, upper stage payload deployment, Raptor vacuum restart, and non-catastrophic reentry with flap damage, that SpaceX can credibly start thinking about a full orbital attempt on Flight 11. At the same time, the company is already pivoting to V3 hardware with Raptor 3 engines, higher performance, and modified structures that will not perfectly match the behavior of the test vehicle everyone just watched. That is why this flight feels like both a capstone and a springboard. It is probably the last time a V2 Starship will be used to chase so many firsts at once. The next major narrative shift will be toward routine orbital missions, propellant transfer demos, and eventually tower catches where the Mechazilla arms attempt to grab both booster and ship out of the sky. Elon Musk has indicated that the first catch attempt will likely happen somewhere between Flight 13 and 15, which suggests that Flight 11 and 12 may serve as final dress rehearsals for precision targeting, thermal margins, and Raptor restart behavior. Flight 10, then, is best understood as a deliberate stress test of a soon-to-be-retired configuration. It proved that the system can lose an engine at max Q and keep flying, that the booster can handle a high-drag return without buckling, that alternative landing engine patterns are viable, that the upper stage can deploy payloads and restart in vacuum, and that even after an internal blast and significant flap damage, a belly-flopping stainless steel skyscraper can still guide itself to a splashdown within a few meters of where it was told to go. It was messy in places, but that mess is how the next version gets sharper. For outsiders, it is easy to get distracted by the splash, the fireball, or the strange orange paint job, and miss the quieter story underneath. What SpaceX actually bought with Flight 10 is freedom of design for the next generation. Having seen where pipes bend, where tiles crack, where metals rust, and how guidance behaves when symmetry is broken, their engineers can now lock in or discard ideas with real confidence instead of guesses. That is what a maturing launch system looks like in engineering practice.